Hello and welcome back. The next module is on verification. Verification is a very important part of design. You as a designer have a responsibility to find as many bugs as you can and eliminate those bugs from your design before releasing it into the system level models for the chip. This is as true whether it's an FPGA or whether it's a standard cell design, but it's even more true for a standard cell design because the chip has to go to fab being as bug-free as possibly can due to the expenses of that. So this section is meant to deepen your knowledge about verification and the construction of test benches for verification. We're going to cover why it's important, richen your tool set to do your own designer-driven verification, talk about metrics, talk about more formalized project-wide approaches to verification, and finally introduce you to System Verilog, which is the language that is used for system-level verification. References that I've used are at the bottom of this page. So why do this? Obviously, you want to remove as many potential bugs from your design as possible before sending the chip out for fabrication. Frankly, even before sending the chip into the group level build that builds the RTL for the chip as a whole. And you do this by doing lots of simulation, mainly of the pre-synthesis Verilog, and of course in Verilog. This is particularly important for a standard cell design. Chip fab is very expensive, millions of dollars to build the mask and get the first parts back from the factory. And if there's a bug in that, you have to do all that again, rewrite the masks, redo the design, and this takes a lot of time as well as money. And time can be particularly valuable because if your competitors don't need this iteration, their product will be on the market before yours, and that eats into a lot of your potential profit. Even though it's very critical for standard cell designs because of this cost and time of getting hardware back from the fab, it is still pretty important for FPGAs. Yes, the iteration time in FPGAs is faster, but nonetheless, it is a lot harder to use actual hardware for debug than to use a simulation. So it behooves you to excise as many of the bugs as you can from the simulation before building hardware and trying to work out what's going wrong. So in this module, as well as covering the importance of verification, I'm going to give you different ways of building test benches, including additional code constructs for both the synthesizable, for testing the synthesizable design and for constructing the non-synthesized blocks that have to be connected to your design, such as memories and so on. Talk a bit about assertions and formal verification, and then system verification using the System Verilog language. I want to briefly discuss with you the origin of the term debugging. It's actually a little bit of a myth that the term debugging arose with the early computer industry, with the early university-based computers that were used to calculate artillery tables and so on. In fact, the term has been around for quite a while. For example, early aeronautical engineers would talk about getting the bugs out of their airplane design. But nonetheless, one of the early computers, the Harvard Mark II computer, was built out of relays. And one particular programmer found a dead bug stuck in a relay and used this to recycle the term to computer science. So debugging code of any form has become a widely used term, but the origins in the field of computer on the right there, that's the Mark II computer. It's not really a programmable computer like you'd run Fortran on or anything like that. It's really a big artillery calculator. And the documentation for the dead bug found in the relay is down below. And you notice, first actual case of bug being found, recycling the term. So verification is a very important part of any design. In a standard cell design, it can consume the majority of the design resources. That is, consume more resources than the design itself. And I'm talking here about computers and compute cycles. It's even more than 60% of those. But even the team, a large number of the people in the team are devoted to verification. Verification is done with the pre-synthesis code. though there are things that are done with the post-synthesis netlist to make sure it's correct. And I'll talk about formal verifications, one of those steps that are done for that later, specifically model checking. As chip sizes grow, the number of gates you have to verify grows with the chip size. And this is true whether you use intellectual property, that is other people's designs or your own previous designs, or not. You might reuse designs in order to reduce the amount of design effort. Unfortunately, it doesn't reduce the amount of verification effort, particularly at the chip level as a whole. That is because you still have to test the interfaces between the existing designs and the new design to make sure things still work correctly. So in a sense, the amount of verification that has to be done on the chip grows with the number of transistors in the chip, whether those transistors are newly designed for this chip or reused from a previous design. Now, in this set of notes, I'm mainly dealing with verification for an individual designer. In the follow-on course at NC State, EC 745, verification with System Verilog, there it will deal with chip-level verification using the System Verilog environment, which has a lot of C++ aspects in it, and is a very valuable skill because there's actually a shortage of these people out there in industry. But despite the fact there is a system-level verification team using formal, fairly sophisticated methods, the designer still has to conduct quite a bit of verification of his or her modules to try to excise as many bugs as they can. There's other things the designer might have to do to support verification. For example, particular coding practices. Good use of comments is one here. Comments should, for example, explain the functional intent of blocks rather than write out code in English, which is a common neophyte error in writing comments. Comments should be describing functions of blocks, not behavior of individual code. Assertions are a method that designers can be used to aid in verification. I'll be talking about that later. Sometimes the designer puts in features in the RTL that aid in verification. For example, being able to start a long finite state machine in the middle of a specific deep state sequence. Instead of being forced to start from the reset every time, it might take many tens of thousands of cycles to get to the point where someone is trying to remove a bug, and this can be useful to get to that point quickly. Nonetheless, there is often a separate verification team, particularly on standard cell chips. There are several reasons for this. This team works at the chip level. Doesn't focus on the module level. The designer is still responsible for the modules. But in doing so, that team can find bugs across designer boundaries and can also find bugs left over from the designers themselves. And this is one reason why a separate team is valuable and a separate methodology is valuable. You must experience this yourself. When you're specifying the details of design, you go and code it. You sometimes carry incorrect assumptions in your head that you don't necessarily question. They end up being bugs in the design that you find difficult to get rid of because they're essentially part of your assumption set. It's very hard to think in two different ways with you or the person doing both the design and the verification. A separate verification team doesn't have this problem. They might find these dumb assumption mistakes the designer might not find. Increasingly, the separate verification team uses its own tools and methodologies, such as System Verilog, which we'll describe at the end of this module. One thing to realize is that it's actually very difficult to eliminate all the bugs from the design. In fact, most chips are sold with bugs in them. What these bugs are actually often present in are features that they decide just not to support because they know the bugs are there. But nonetheless, it is very hard to get rid of all bugs. Thus, you need as many different ways as possible to discover those bugs in normal verification. And in this submodule, I'm going to be talking about some of those different ways in which we get to find the bugs. This includes using quite different tools. Simulation through test fixtures, the focus here. Assertions, which I'll talk about later, is a separate way to find bugs. Formal verification has its uses in finding bugs. And finally, emulation, which is actually building a version of the hardware in an array of FPGAs, is also quite useful to find those last few bugs. In this submodule, we're going to deal largely with simulation through test fixtures. The basic idea is you want to apply vectors to your design and observe the outputs in some of the internal nodes for correct functionality. This means you've got to think of ways of getting those vectors that give you as many different avenues of attack as possible. And you've also got to think about how you're actually going to observe the outputs. Particularly as observing a screen with a bunch of waveforms on it is not necessarily the best method. And finally, in the next submodule, we'll talk about some of the coding styles, besides the ones you've seen, that might be useful for writing test fixtures. So next thing I want to do is talk about the different sources of verification vectors. Again, it's important that you identify multiple ways of getting verification vectors. If you rely on only one way to get verification vectors, then you're quite likely to have a lot of bugs left in your design because you haven't had as many different avenues of attack on finding bugs as possible. And in fact, class projects in this class most probably have a lot of residual bugs because the test vector generation is usually just one straightforward method. Most designers start off with thinking about the expected functionality of their design and creating vectors that produce that expected functionality. And this is a reasonable way to start, but it's not necessarily addressing all the bugs in your design. It just won't identify all the bugs in your design. In this functional approach, you also tend to prioritize things. You start with those things that must work, and then get down later to those features that you would like to work. And in fact, this even happens at the system level. Again, a lot of chips are actually released with bugs in them, and what they do is they simply remove the features that have those bugs from the documentation for that chip. One side effect of this, by the way, is quite often end users discover these hidden features and publish ways to get access to them. So be careful, these hidden features don't come with a guarantee of being bug-free. Another source of verification vectors is from a higher level model. That is, you have a C-level model that runs for your chip as a whole. For example, a complete video compression model. And you can use this to generate input and output vectors for your particular submodule. For example, part of the C model for an MPEG encoder would actually run the motion estimator. And that will produce sample inputs and expected outputs for the motion estimator that you can then apply to your design. This C-level model of the chip as a whole is referred to as a reference behavioral model, or quite often more simply as the golden model. It is the baseline of a working representation of the functionality of the chip that can be used for comparison against other representations of the functionality of the chip, such as the RTL. Another really good source of verification vectors is to produce vectors that deliberately test the parts of the chip that are difficult, particularly the parts that were difficult to design. If it was difficult design, it's more likely to have bugs in it. Another aspect of this is actually producing vectors to increase the quote-unquote coverage of the design. I'll talk about this later, but during simulation-based verification, you can instrument your tools so as to measure things such as how many lines of code have been exercised, how many branches have been exercised, how many paths through your design have been exercised. And sometimes you actually write test fixtures specifically to test parts of the design that have yet to be exercised. Same is true at the functional level. Has every end-use function been verified? And again, there's a prioritized list here that people go through. Another good source of simulation vectors are random vectors, or more specifically pseudo-random, since we don't have a true random number generator on most computers. The idea is you generate a set of random input vectors, say random video shots for the MPEG encoder. You run those through the golden model, the reference model, the C model, for that is a pure software simulation of the entire chip functionality. You get the results from that C model and compare them with the results you get from the RTL simulation. Finally, particularly for the system level simulation team, running system level test vectors, that is actually running the chip on its expected functionality and pseudo-random vectors at the system level, simulating the chip in its entirety, is very important. As I said, there's a separate team that does this once all the RTLs get together. But sometimes individual designers do that by integrating their RTL with a C-level reference model using what's called PLI, or Programming Language Interface. So for example, again for the MPEG encoder, you might actually get the C version of the entire video encoder from someone else, rip out the motion estimator, use PLI to connect the C-level model with your RTL, the motion estimator, and run real video through the codec to see if you get what you expect to see. In addition to doing this, you'll also need models for the parts of the chip that aren't synthesized, such as the memories. You need Verilog, not synthesizable Verilog, but Verilog for the interfaces that capture the behavior of these functions, so you can do this system level simulation. So you apply your vectors to your design. How do you observe correctness in the output? Now, of course, you can look at things in the waveform viewer, and the waveform viewer is very useful, particularly for debug. But it's not very useful for checking that everything works. So let's see, on cycle 100,229, this signal is meant to go high. I'll scroll through the waveform viewer to that cycle and verify that as one check to make sure it's working correctly. Doing that each and every time you change the design will get very, very tedious. One thing you can do is add assertions to check for specific features. We'll talk about this later, but even there, that's not used for everything. What is more useful is to do some checks in the test fixture to analyze the results that inform you of correctness. One way of doing this is just collecting vectors on the outputs and see if they are what you expect to see. Another way is to put features in your test fixtures that actually look at specific signals to see if they're behaving correctly. And I often do this in the early stages of designing a module. So for example, you've already seen one of these in the simple counter we had. At time 28, we looked at the 0 flag and displayed to the screen whether that passed or failed. Though normally you wouldn't display the pass, you'd often normally just display the fail. You can generalize upon this even further by calculating within the test vector, in the test fixture, what the expected result is. For example, here, if the data going to the countdown timer is 4, you expect it to take 40 nanoseconds to reach 0, so you calculate that. Then do this hash expected delay. Hash delay functions can be, in test fixtures, can be variables. And at that time, look at the 0 flag. This way you have a test fixture that not only checks the code automatically, but includes understanding of the code behavior and uses the fact you have code to calculate things that you expect to see from the test fixture. So that brings us to the end of this first submodule. Again, I'll remind you that even though there's often a separate verification team that does system level verification, you as a designer are still responsible for verifying and debugging your own designs. For this, you need as many different sources of test vectors as you can get to maximize the probability of discovering bugs in your design. You can get test vectors from the expected functionality, from a higher level module. Sometimes you will add test fixtures to specifically exercise parts of the design that haven't been exercised yet, for example, as measured by code coverage. You might generate pseudo-random test vectors and compare them against results from a higher level model. And you might simulate design as a complete part of a complete system simulation using the programming language interface to interface your Verilog to a bunch of C code representing the rest of the design. A common metric that's used at the designer level is code coverage. That is the percentage of the lines that have been exercised to date and percentage of branches and sometimes even paths taken through the design. And again, you'll often add code to at least get the percentage of lines covered to 100%. You might measure functional coverage, that is, what functions have been fully verified to work as expected. And finally, I urge you, for your own sanity, more than anything else, to strive to create test fixtures that don't require you to look at the waveforms that are coming out, except as an aid to debugging. That ends this particular submodule. In the next submodule, we'll look at code constructs within test fixtures and connected components that might be very useful to you. Thank you very much.